Hello, curious minds. If space is only 100 kilometers above your head, why is it harder to reach than the opposite side of the planet? Many people imagine space as a kind of ceiling above us, like you could just keep climbing until you reach it. But here's the tricky part. Space isn't a floor you step onto, it's just where the sky ends and the atmosphere thins out. Even at the official boundary of space, 100 kilometers, or 62 miles up, the Kármán line, which is the red line on the picture, Earth's gravity is still pulling you down with about 97% of the strength it has at the surface. So simply going straight up doesn't make you weightless, it just makes you high. In fact, spacecraft in orbit, whether it's a tiny CubeSat, the International Space Station, or a communications satellite, stays up there not because gravity stops acting on it, but because it's moving sideways so fast that it's constantly falling around the planet instead of into it. That's why space travel is all about speed, not just height. Okay, so why do astronauts float in space? Is it because there's no gravity? Not quite. Gravity never really stops, not even hundreds of kilometers above Earth. In fact, the International Space Station still feels about 90% of the gravity we feel on the ground. So why does it seem like astronauts are weightless? It's because they're moving sideways so fast that they're constantly falling around the Earth, creating the sensation of floating. And it's the same for every satellite space telescope or orbiting spacecraft. They're all in free fall, trapped in Earth's gravity, but never hitting the planet. Here's the mind-bending part. Getting high isn't the hard part. Getting into orbit is all about speed. To stay in orbit, a spacecraft doesn't just need to climb above the atmosphere, it needs to move sideways at about 28,000 kilometers per hour, or roughly 17,500 miles per hour. That's fast enough that as it falls toward Earth, the planet curves away beneath it, so it never actually hits the ground. Think of it like throwing a baseball. If you throw it lightly, it falls to the ground quickly. Throw it harder, and it travels farther. Throw it fast enough, and it starts to circle around the Earth instead of landing. Hitting that perfect sideways speed is what keeps satellites, the ISS, and even tiny CubeSats floating safely in orbit. It's a balancing act, and without enough speed you'd just come crashing back down. Once a rocket leaves the launch pad, it might seem like all it has to do is keep going straight up, but here's the catch. Hovering in space is practically impossible. Gravity is constantly pulling the rocket down, so to just stay in place, a rocket would need to burn enormous amounts of fuel non-stop. Far more than it can realistically carry. And then, there's the atmosphere. In the lower layers of the sky, air isn't empty. It's full of tiny particles that push against the rocket, creating drag, which pushes against the rocket and slows it down. Fighting both gravity and drag by going straight up is incredibly inefficient. Rockets would burn up or run out of fuel long before reaching orbit. That's why rockets don't just blast straight to the edge of space, they perform a gravity turn, gradually tilting sideways as they climb. This lets them build the sideways speed needed for orbit while minimizing the energy wasted against atmospheric drag. In other words, by going slightly sideways instead of straight up, rockets use physics to do most of the work for them, saving fuel and making orbit possible. Wow, so next time you look up at the sky, remember, reaching space isn't just about climbing high, it's about moving fast enough to fall around the Earth. And here's a question for you. If you could design a spaceship, what clever trick would you use to make getting to orbit easier? Drop your ideas in the comments. If you enjoyed this journey, don't forget to like, subscribe, and hit that bell so you never miss an adventure beyond the stars. Thanks for watching. Until next time, keep looking up.